heuristic for optimal planning.
Thank you, Gabi. So my name is Menkes van den Briel. I'm at NICTA, National ICT Australia, also affiliated with the Australian National University in Canberra, Australia. This is joint work with Blai Bonet at the Simon Bolivar University in Caracas, Venezuela. So this talk will be about a linear programming-based heuristic for optimal classical planning. In particular, about how to strengthen this LP by adding constraints derived from action landmarks and fluent merges or variable merges. The outline of my talk is sort of as follows. I'll talk about this base linear programming model and talk about how what constraints we add to strengthen this model, present some results and conclusions. But first, I'd like to start with a bit of background and motivation as to what motivated this work. So really, this paper combines ideas that are presented in two papers. Blai's ICAPS 2013 paper and the CP 2007 paper written by myself, Jay Benton, Rao Kamampati, and Thomas Vossen. The one thing these two papers have in common is that they both describe a linear programming model based on the SES plus formalism. In SES plus, a SES plus planning task, you have a set of variables V and a set of actions A, where an actions is defined by its pre, post, and prevail conditions. Here we have a slide extension where we also consider cost. So C is a cost function that applies a non-negative cost for each action. In SES plus planning, we have variables, and so given a variable x can be represented by a domain transition graph, where the nodes in this graph represent the feasible values given by dx, and the transitions in this graph represent the feasible transitions in this graph represented by t of x. But probably the easiest way to get a bit of an understanding is to simply look at an example. Very simple logistics example, one package, one truck, two locations. We have two variables indicating the location of the package or the location of the truck. Package can be at location 1, 2, or inside the truck. The truck can either be at location 1 or 2. In this representation, the in arrow indicates the initial state, and the extra circle indicates a goal state. So we want the package to be at location 2, and we don't really care where the truck ends to be. It can be either at location 1 or 2. And so given these networks, or given these domain transition graph, we derive a flow model. We introduce a flow variable that maps action labels to real valued variables. And the objective is to minimize total cost, minimize the sum of the action cost, subject to this constraint. And this constraint is a flow balance constraint that we have for every node inside the different networks. And basically, this balance of flow constraint tells us if you delete a value, if you delete an atom, you must add it. If you delete an atom 10 times, you must add it 10 times. I should say that this strict balance is not quite true. If you have an initial state that is not a goal state, then in fact you delete that value once or exactly once more than you add it. Or if you have a node that is a goal state but not an initial state, then you must add that value exactly once more than you delete it. I should also mention that this equality is also not quite true. Sometimes this has to be an inequality constraint. And this is due to incomplete actions. An incomplete action is simply an action that has a post or a post condition on a variable, but not a precondition on a variable. But I'll leave out the details. You can look those up in the paper, but the inequality is due to these incomplete actions. So the first result, the solution to this base model can be used as an admissible heuristic for planning. And probably the way to see this is to simply project a plan on these constraints. And you'll realize that any feasible plan will satisfy this balance of flow constraint. Any feasible plan that deletes effect must add that effect. Any feasible plan that deletes effect 10 times must add that effect 10 times. Apart from this initial goal state, and you have to be a bit careful. So Blai's ICAPS 2013 paper shows that that heuristic is already effective and efficient. The table here shows you coverage, the number of problems solved in planning competition domains. Orange indicates the heuristic that was better, or that had best coverage. And here we're comparing this base heuristic with LM-cut. It is effective because, I mean, coverage, okay, the coverage, there's quite a big of a gap, but if you ignore the myconic domain, that gap narrows down already by almost 90. And this heuristic is efficient, solving literally 1 million LPs throughout your A-star search is not that big of a deal. The same observation of this heuristic being effective and efficient was also observed in the CP 2007 paper. The base heuristic here is indicated by this LP minus. I should mention, though, that these are not domains, but these are planning tasks. And this is not coverage, but it's the heuristic value at the initial state. Opt indicates the optimal distance estimate from initial state to goal. H+, the optimal delete relaxed planning heuristic. And you can already see here that this base heuristic pretty much or reasonably approximates H+. I should say, though, that the observation that this heuristic was efficient and effective wasn't the only observation made in the CP 2007 paper. Quite the contrary. In fact, the main observation of that paper is that this base heuristic is actually quite weak and can be improved significantly if you add constraints derived from fluent merges. And this is the base model added with fluent merges. You can see that this base heuristic increases significantly and, in fact, improves most of the time over H+, which was, I think, until quite recently, sort of being considered as the holy grail of admissible heuristics for optimal planning. Even further, in quite a few of these cases, this heuristic approximates the perfect heuristics. So that's also actually quite nice and interesting. So we have this base heuristic that's effective and efficient, yet can be improved significantly. Blai notes that we can add constraints derived from action landmarks. The CP paper notes we can strengthen it by adding constraints from fluent merges. So let's look at both of these, and we'll first look into landmarks. An action landmark L, or landmark for short, is a subset of actions such that every plan P contains at least one action in L. With that definition, we can already derive this constraint, that the sum of the actions inside the landmark must be greater or equal to 1. I should say, though, that a landmark is state-dependent, and so we have to add this constraint at every node, and we have to remove it once we've added it. So it's really, it's a constraint that we add and remove throughout the search. So the second observation we have is that the set of landmark constraints is admissible. Okay, well, that's not quite new. But as a result, the solution to the base model with landmark constraints, H base L, can be used as an admissible heuristic. And again, project any feasible plan onto the constraints from the base heuristic, the balance of flow constraints, as well as the landmark constraints, and you'll find out that it'll always satisfy those constraints. Another observation here is that the base constraint with landmark constraints dominates the heuristic, the optimal cost partitioning with the same set of landmarks. This may be a bit trickier to see. I have a spare slide towards the end. But really, I mean, here we're solving this set of constraints with an objective function, but this is already implicit in this heuristic as well. But more details, I have an additional slide. Just to see, have a bit of an idea of how this performs. The graph on the left shows you the heuristic value at the initial state. Above the diagonal is where the base model plus landmark constraints derive with the LM cut landmark constraints versus the base model alone. And you see that the heuristic value increases significantly. And because of that, the number of expanded nodes goes down. This doesn't necessarily mean that we solve more problems. Because of the additional constraint, we may take extra time and therefore not be able to solve the problem within 30 minutes. But as you can see, the coverage compared to base to the different set of landmarks, landmarks by Zhu-Givan or using the landmarks derived from LM cut, we increase coverage significantly. Let's look into merges. Merges really sort of combines two or more variables into a single supervariable. In a way, it's taking the Cartesian product of these variables and creates a new variable. The good thing, though, is if we have a new variable, we can really impose, again, just new flow balance constraints on that new variable. The one thing, though, is that as soon as you merge, you can blow things up. And one difference here is, in fact, I mean, here we only had one drive from 1 to 2 action. In this variable, we have 3 drive from 1 to 2 actions. This is what we call an action copy, and this is something additional that we have to deal with. But really, in short, a merge combines 2 or more variables into a single variable. But this merge variable simply introduces more balance of flow constraints. We also have to take care of this constraint that links the original action label with the copies of that action label. The next observation is that the set of merge constraints is admissible. And as a result, the solution to the base model with these merge constraints can be used as an admissible heuristic. Again, I mean, this is just, it's a new variable. I could have had this variable from the start. But again, just project a plan or any plan onto these constraints, and you'll find out that it'll satisfy these constraints. The one thing, however, with merging is it gets messy very, very quickly. This is just merging 3 variables with a number of values. So the one thing to avoid is to create the complete merge. You want to merge dynamically or incrementally. So we incorporated dynamic merging, which is literally dynamic in all ways. We incrementally merge more and more variables, but we also incrementally merge the variables. We have a very simple merge strategy where we take the prevail condition, where we merge the prevail conditions with the preconditions of an action. And again, probably the easiest way to look at that is through an example. This is our initial, we set constraints for these 2 variables. We solve our LP. This is the solution. We load and unload. We don't have to drive. We now merge the precondition with its prevail condition. And we do that also for this action. We merge the precondition with the prevail condition. So we only add 2 constraints rather than all the 6 constraints. And this reduction can be far more significant if we have far bigger variables. So once we add those constraints, we solve the new model, and now we realize that we have to drive to pick up the package, drive back to deliver the package. And this, in fact, gives us the perfect heuristic for this simple example. For results, we implemented in fast downwards. In the experimental setup, we basically copied what is being used in the planning competition. 2 gigs of memory, 30 minutes. We're using Cplex as the LP solver, and we're comparing a variety of heuristics. LM-cut, optimal cost partitioning based on LM-cut, our base model, versus our base model added with landmark constraints and merges constraints. Again, this shows coverage. I'm highlighting sort of the columns that are of most interest. I'm just going to the next slide. We can see that the best coverage we get is when we have the base model, we add the landmark constraints, and we add the merge constraint. It gives us the highest coverage. But I should note that none of these heuristics is dominant. Even the base model has a higher coverage in some domains. One last thing I'd like to point out is even though LM-cut, our base model with LM-cut dominates these other heuristics, it actually doesn't dominate in coverage. Again, this is due to calculation time. Quick look at results. This is our base model with landmark constraints and merge constraints. We're comparing it with LM-cut. We get better heuristic estimates, and therefore fewer nodes are expanded. However, we generally take more time. So we really use the 30 minutes more than LM-cut. To conclude, flow-based heuristics are effective and efficient, yet can be improved significantly. Dynamic merging incrementally merges more and more variables, and currently we've only incorporated a very simple merge strategy. I really want to stress out flow-based heuristics provide a rich area of future research. I highly recommend to stay here for the next session where Florian will talk some more about flow-based heuristics. But I also want to highlight just using LPs for heuristics for planning is a good area of research. And this we see in the work by Tatsuya and Alex, the work that they presented in the workshop earlier in the conference. That's it. Thanks.
Thank you. One thing that you didn't mention was the need for a merge strategy, right? Correct. You have to select merges, decide what to merge, what not to merge.
Yes.
Any comments on that?
I'll
rephrase my question. The results, empirical results, were they like optimized in terms of merge domain by domain, or some default strategy that you picked and used it throughout the work?
Default, naive strategy. Nothing special. There are indeed clever ways to merge, and ideally you want to use the solution that the LP provides and derive a cut or a new constraint or a merge that will actually make sure that that solution will not be generated again. This is, I think, really the bullet point of what are good merging strategies. I have some ideas, but it's still sort of, half-baked.
So you made the point that the partial merges, let's call them that, like not producing the full cross product. That would save a lot of computation time potentially and so on. But did you actually try to look at that experimentally? Like, does this actually happen, or How important is it? Can you say anything on that?
So the 2007 paper creates the full merge, and there sometimes, at least for the larger problems, it would take up to 15 minutes. But by merging dynamically, we can get at least, we can solve these problems in a matter of milliseconds or seconds.
I would like to add something to that. Yes, I tried that before, like getting more in touch with Menkes, and it doesn't work. It explodes very quickly. It will generate an NLP that it will take forever to solve, so that doesn't work. So you need to do this incremental merge.